that you can hear me.
Sì, sì. Buongiorno.
Okay. Can you see the blackboard, the whiteboard?
Sì.
Okay, so we're continuing with our discovery of reaction rates and non-equilibrium processes, okay, and how fast reactions proceed. And no, it's funny that I'm looking at the other screen and I have a computer program that is running. I may eventually show you something what you can do computationally, and it's running exactly this. Okay, it's running a program that calculates. Well, it's also a fluid dynamics program, but it calculates the rate of reactions of a complex chemical system, and it evaluates all the concentrations instant by instant. So it integrates the equations that we're going to build, by the way, very soon. Anyway, before we do that, let me just recap a few things. If you remember, we had written down a generic global process. We call this global. There is a reason for that. I have to activate my... Okay. This is a global reaction. Okay, and we use this word to distinguish it from what we had started writing the other day, from an elementary reaction, and we'll see what the difference is. But in general, if you have a global process, okay, like this, the rate of reaction, you can write it in terms of rate constant, and then the product of all the molar concentrations to the power of these reaction orders, okay? And generally speaking, we said that these reaction orders, alpha and beta, are not the same as the stoichiometric coefficients, okay? Then we introduced the concept of the overall reaction order, which is simply the sum of these exponents, okay? We took a look at the units. This is quite important to understand. The units of the rate constant changes, the units change depending on the overall reaction order, okay? And in fact, pretty interestingly, if the reaction order is 1, then this rate constant acquires the meaning of 1 over time. So it's a time constant. So it is indicative of a time scale, okay, of the process, but only when the reaction order is 1. Okay, otherwise you have this complex units. Okay. Now, why do we term this reaction global? Okay. Well, I said to distinguish it from an elementary reaction, but what is an elementary reaction? Well, the global process is really an overall, okay, representation of what is going on. Okay, it's a macroscopic representation of several, okay, elementary reactions, which are actually, okay, a representation of collision, of actual collision processes between molecules. So the global reaction is really not, okay, a collision between A molecules of A and B molecules of C, B, and so on. Okay, it's not. It's a global representation of the kinetic process, okay? But really it's hiding, okay, a series of steps which are actual, okay, collisions between molecules. And those collisions, okay, acts of collisions we call elementary reaction, okay? And I'll give you some examples, okay, of what an elementary reaction is, okay? The number, okay, of molecules or atoms which are involved in each of these elementary reactions, okay, is called molecularity, okay, molecularity. Believe it or not, this is what I wrote here. Now, obviously, as I said, imagine an accident between cars. Generally speaking, you can have an accident occurring with one car, okay, kind of flipping and doing its own thing, okay, or you can have a collision between two cars, okay. Very rarely, I think you can have a collision between three cars at the same time, okay. So really, elementary reactions, the molecularity is really either 1, 2, or 3. We'll see the special case of 3. Okay, so you have molecular, bimolecular, and trimolecular elementary reactions. Not more. Okay, it becomes exponentially, let's say, unlikely that you have these kind of collisions between molecules. Okay. Unimolecular reactions, generally speaking, they can be either well, purely unimolecular is, for example, something called isomerization. For example, this is an example. I'll just give you random examples. So this asterisk basically means that this is the energized or excited version of this molecule, okay, which isomerizes into essentially the same molecule with the same formula, okay, but different internal structure. So I won't get into too much detail here, just to say that this involves one single molecule, as you can see, okay? And if it absorbs some energy, then it will isomerize into this new molecule, okay? I have to let someone in. Can you still see the whiteboard?
Yes, Prof.
Okay. You can also have things like well, we'll see them later, but unimolecular reactions can also be called dissociation reactions, okay? Things like, for example, I'll just give you the symbolic version, okay? Where you have essentially one molecule kind of breaking up, okay, into two. These are, I'll just put a bracket here because these are very tricky reactions, okay? And we'll see that they can behave either unimolecularly or bimolecularly, depending, in fact, on the pressure. And this is one of the examples that keep it in mind. But this is the purely unimolecular behavior. Okay, this is a little bit more tricky. So it depends on pressure. These are the pressure-dependent reactions. Clearly. Let me just be clear on this. When I write down the reaction rate, which by definition, okay, is in this case the rate of change of the molecular concentration, okay, of this molecule, okay. Okay. Bear in mind that I'm always considering, right, irreversible reactions, okay, to make things easier. By experiment, we find out, okay, that this is essentially a reaction rate times the instantaneous, okay, concentration of the molecule. So you see that the stoichiometric coefficient is 1. Okay, it completely coincides in this case with the exponent here, okay, the reaction order. In elementary reactions, okay, we always have this kind of behavior, okay? We always have the correspondence between the stoichiometric coefficient and the reaction order. Let me give you another example, a bimolecular reaction. So, for example, this reaction here, atomic nitrogen, nitrogen oxide giving N2 plus O, okay? This is an actual elementary reaction, so it's a collision between an atom of nitrogen and a molecule of nitrogen oxide, and it's elementary, okay? And so the reaction rate, which is, for example, this rate of change, okay, it's also this, okay? These are the definitions, okay? Remember that I am doing, I'm putting here 1 over the difference between the stoichiometric coefficients, remember? So this is 1 over 0 minus 1, so it's minus 1. So by experiment, okay, we find that this can be written as the rate constant, which will be obviously different from any other reaction, obviously. And then the product of the concentrations of N, okay, and NO. And again, as you can see here, stoichiometric coefficient 1, stoichiometric coefficient 1, reaction order 1 and 1. Okay, these are the elementary reaction and how they behave. Okay. A special case of trimolecular reaction. Well, these are these are a breed of their own in the sense that typically the trimolecular reactions involve what we call the third body. What's a third body? We always, it's a molecule, okay? It's a third molecule, which we always refer to as M, okay? M meaning it could stand for any molecule, okay, present in your system, okay? And so, for example, I'll just give you an example, like this reaction with the chlorine atom and a third body, okay, actually giving out the chlorine molecule, okay, plus M. So you see what happens with this M. It does not take part, okay, molecularly, it does not take part in the reaction. It only participates in the reaction energetically. So this collision here, okay, energetically will cause the chlorine atoms to fuse together to form the chlorine molecule. Okay, but M, okay, now it's probably now in a different energetic state than it was here, okay, but it didn't change its molecular structure. And M again could be anything. M could be Cl, it could be Cl2, it could be any sort of molecule that's actually present, okay, in your system. But it will have, depending on which you choose, okay, which one actually operates in this particular collision, okay, it will do so with a different efficiency. Okay, I won't get into too much detail here. So when you see an M, okay, in a reaction, that's a third body, and it's a molecule that is present, okay, that participates energetically in the collision, okay, but does not participate chemically, okay. Now, if you write down the reaction rate, by definition here, it will be something like 1 minus a half, so 0 minus 2 is the stoichiometric coefficient of chlorine atom, rate of change of molar concentration of Cl, Okay, this experimentally, so you can write down now what the rate expression is. We kind of found the pattern here. You still have a reaction rate. Then you have essentially the product of the concentration of this third body to the power of what? To the power of 1, because this is an elementary reaction. And then the concentration of Cl to the power of 2, okay? Now, these reactions are particular reactions in that you see that there is this factor here, the rate constant times the concentration of this third body, which does not participate in the reaction. This, in fact, could be absorbed into a new constant, which is typically, and we'll see this later, a function of pressure. Because as you vary the pressure, the molar concentration of this third body will change, okay? And we'll see this far more rigorously. So these, generally speaking, these third body reactions are generally reactions that tend to depend, okay, on pressure, okay? So this is sort of a reaction, pressure-dependent reaction constant, okay? But anyway, what's really important here is that both, well, not both, it's that for unimolecular, bimolecular, and trimolecular elementary reaction, you see that the exponent here in the rate expression, okay, is always equal to the stoichiometry. If you want to say it in more compact form, you can say that in elementary reactions, okay, the overall reaction order n, okay, so that, remember, is the sum, okay, of all the exponents. So this, in this case, it would be 3, in this case, it would be 2, and in this case, it would be 1, is actually equal to the molecularity. Okay, the number of molecules involved in the collision, okay, in the actual reaction, okay? Now, the fact that you can actually derive the expression of the rate constant, not the rate constant, sorry, the reaction, omega, directly by looking at the stoichiometry, okay, is quite surprising, okay, in the sense that you can deduce it immediately. You don't even have to do any sort of experiment. You're given a elementary reaction, okay, and you can directly deduce, okay, the reaction rate, the rate of reaction. So let me generalize this. If you have an elementary well, I'll stick to the irreversible, okay, reaction step. Usually you will use this word step, okay, because in general you have, in a chemical system, you have many steps, okay, many elementary reactions, which, and we can still use our, usual notation. Okay. Well, we know that the reaction rate is 1 over, this is by definition, okay? The rate of change of molar composition of any of your species. And in fact, always remember the dmi by dt, we always call it omega I. Okay, so this is the actual rate of change of the molar concentration of this species I. Okay, and this is the overall, I mean, the reaction rate. Okay. So generally speaking, if you're interested in the rate of change of the molar composition of the molar concentration, all you do is you multiply this factor here by the reaction rate. And what's the reaction rate expression? We just said, okay, this is an elementary step. So omega will be, well, a reaction constant, okay? And then you will have to write down the product, okay, of all these molar concentrations. Okay, so we have a product here on I to the power of, well, reaction orders which are equal to the stoichiometry. So in this particular case, okay, you have the new prime, okay, factors. This is irreversible, so we're not considering the reverse process, which is simpler, okay? And so this is your final expression, okay? Which is very handy because look, what we can do, well, you don't need to run an experiment in the laboratory because we can write it down directly from the stoichiometry. We know what the stoichiometry is. So you substitute this omega here, okay? And now what you have is a set or a system of ordinary differential equations, okay? I hope you can see this. So this is dmi by dt equals some nonlinear, okay, right-hand side, which is a function, a nonlinear function of all the dependent variables. And it's clearly now the solution of this. We can call this, for example, we can have this in the form dy by dt, okay, is equal to some function of y. Okay, this is a typical form of your non-linear ordinary differential equation system, okay? You can add, for example, an initial composition, okay? So it's an initial value problem, okay, that you can integrate numerically. That's why, as I said before, you know, it's very common that you use computers, okay, to integrate numerically these chemical kinetic systems, okay? And you can write them explicitly like this, okay? And clearly, what y is a vector of all the concentrations. So M1, M2, etc. Okay. I'll put a transpose because it's a column. Okay. In other cases, you may have heard of the word dynamical system. Okay. And this is what we're going to be treating this like, as a dynamical system, okay? These kinetic problems. They are typically composed of a lot of different timescales, okay? The timescales are introduced, for example, if they're all unimolecular by these rate constant, okay? And it is a characteristic, okay, and we'll see why later on, of combustion processes that you have extremely fast reactions, okay, living together with slower reactions. And when you have these disparate timescales that can be very different from each other, you have what is called a stiff, okay, ordinary differential equation, system of differential equation, okay, which is a little tricky and a little difficult to solve numerically, okay? If you solve them explicitly, some of you may have done some numerics, you need to solve them with the shortest possible time scale that you have in the system, okay? The fastest one. And that's virtually impossible because we're talking about time scales which are incredibly small, okay? And so you'd need an infinite or very, very large number of time steps. So what you have to do is you have to use some trick, numerically, some solve for stiff, so an algorithm for stiff ordinary differential equation, okay? But we'll get to that, okay? But bear in mind, or try to remember the general mathematical structure, okay, which is a system of ODEs, okay, ordinary differential equations, okay. That's what is going to be our mathematical instrument, okay, to deal with these. Let me just mention briefly the physics behind this. So we've seen for these elementary reactions, okay, over here, that you generally have for the rate, okay, reaction rate, you have a product of concentrations, okay? Now, why do you have this particular form for the reaction rate? Why is it that you have to multiply the product of the concentration times, okay, some rate constant, which we haven't talked about yet? And this can be understood briefly, okay, I won't go into any detail, but can be understood from something called collision theory, okay, which goes back to essentially the kinetic theory of gases, okay? So again, kinetic theory of gases represents collisions between actual molecules. So we are talking about elementary processes, okay? Chemical reactions that are elementary. So actual collisions, not global, but actual collisions, not global processes, okay? So suppose you have an elementary reaction. You can hear me, right?
Sì, sì.
Yes, prof.
Okay, an elementary reaction, very simple, okay? Like this. Okay, so you have a collision between a molecule of A and a molecule of B to form C. Okay, you have to picture the particles as you can have them non-interacting or interacting, but for the sake of clarity, you can have them non-interacting balls. Okay, like little particles bouncing back and forth depending on their temperature. Their kinetic energy will be higher or lower, okay? So they will be vibrating and moving around and bumping into each other. Now, clearly, the rate at which this reaction occurs, okay, how fast this reaction occurs, will depend on what? Well, it will depend on the total frequency of collision. So I have to figure out what the frequency of the collision, overall frequency of collision, is between A and B. Okay, is it 10 collisions per second, 10 billion collisions per second? Okay, and this is what collision theory provides. Okay, and what the kinetic theory provides. I will just give you the result. Okay. So you can write down this total collision frequency here with an expression. I will just write it down, but you'll see that it makes perfect sense, okay? Well, there are a bunch of constants, okay? We'll start from the Avogadro's constant, okay? Then there is another constant which depends on A and B, okay? And this is the so-called section, okay, of reaction. Reaction section. I'll tell you what it is in a second. Then clearly you will have to have some function of the temperature, right? Because the higher the temperature, the higher the vibration frequency. So we expect a higher frequency of collision. And so you will have this expression here. There is a Boltzmann constant here, okay, also. The temperature, as we expected, there's a square root, okay? Clearly, we could derive this, but this is not a course in kinetic theory of gases. There are these pi's here and there because clearly we're talking about spheres. And mu a b is something that is related to the mass, okay, of the system. In fact, it's in a way it's the reduced mass. So you would have to think of mu a and b as having essentially the mass of A plus B concentrated in their center of mass, okay? But, and this reaction section, what it is, well, obviously the frequency of collision will also depend on how big these molecules are. If they're very big, then the collision is more likely. If they're small, it's less likely. So this reaction section is the sum, essentially, of the radii, okay? If you can talk about radii of these molecules, okay? Of these particles. Now, so this is a factor, okay, that makes sense. Apart from the constants, well, it's directly proportional to how big the molecules are, to their temperature, that is, to their kinetic energy. Clearly, it will be inversely proportional to the mass in the sense that the heavier these molecules, the slower they will be for a given temperature, okay? Because clearly we're talking about kinetic energy, so the mass plays a role in the kinetic energy. But also, okay, what else will they depend on? Well, they will depend, the frequency will also depend on the concentration of A and B, obviously. And this is really important, right? So we'll just write down, in fact, the product, okay? So this is the total frequency. Okay, let me just say that this is equal to the total frequency, which makes perfect sense. So I just cited a result of kinetic theory, but it makes total sense. Okay, this is, by the way, we can write this as just the number z. Okay, so we can write it as z times A times B, and this is usually called a frequency factor. Okay, so it depends on the kinetic energy, so T divided by mu, their size, and their concentration. The more molecules you have per unit volume, the higher will the frequency be between A and B. Clearly, you have to write down the product, not just one or the other, because what counts is the product of the concentrations, right? Because you have to have both of them either high or low. If you have one of the concentrations pretty low and the other one very high, the frequency of collision will still be very low, right? So that's why you have the product of these two, okay? Now, think about it. Is this now our expression of the rate of reaction? Well, it's very similar. I mean, look at this, omega. You have some constant, and then you have a product of these concentrations here. But in fact, that's not the whole story, and I'll just introduce it here. I will introduce the concept here, but I will be more specific in a subsequent class. I will introduce the concept of the Arrhenius kinetics, okay, right now, because this is the total frequency of collision. But that does not mean, okay, that every collision is energetic enough to be completed, for the reaction to be completed. So look at the collision between A and B, okay? You need a minimum amount of energy above which A and B can form C. But below that kinetic energy, okay, the collision will not be energetic enough to form C. So in fact, you have to take this number here, which is the total number, okay, the total frequency, sorry, okay, and multiply it by some fraction, okay, of the overall molecules. So it's a number between 0 and 1, okay, a fraction of the overall molecules that actually have enough energy. And I will just cite the result, okay, very briefly. I will get to it in much more detail later on, but think about it. We have a distribution, okay, of kinetic energies, which, or temperature, if you will, which is Gaussian. This is what usually the kinetic theory of gases really is, okay? So there is going to be very few molecules with very high energy and very few with very low energy, and then essentially an average kinetic energy over here, okay? So how do I get the fraction, okay, of molecules that have energies that are bigger than a certain threshold? I have to integrate this function, okay? I have to integrate it, and I get a function which is like this, okay? Between 0 and 1, okay? Okay, I will just cite this result. Okay, this is what you get analytically as the function. So as the temperature increases, you have more and more molecules, okay, having essentially energies that are bigger than this quantity here. This is called the activation energy. So generally speaking, omega, okay, you take the frequency factor and you multiply, you take the overall frequency and you multiply by this factor here, okay? Okay, this is the so-called Arrhenius form of the reaction rate. And this is what we call reaction constant, K. You see K is a function of temperature, okay? And a very nonlinear function of temperature, okay? So it's this frequency factor, okay, which depends essentially on the shape and partially on the temperature, also on the mass, okay, on the kind of molecules, and then times this fraction which says, okay, out of the overall frequency, you only have to take the portion, the fraction that is energetic enough, okay, to complete the collision, and then A and B. And this is your final form. So I've introduced it. I'm going to get back to it. So that you know where the Arrhenius form comes from. So I have very few minutes. I just want to talk about, in these 5 minutes, I want to go back and talk about the global process, because we talked about elementary reactions now, but what about this big sort of global process here, right? That we've introduced the other day. Okay, let's draw a line here. Now, this is absolutely not an elementary reaction. As I said, it's a global reaction, right? For this, we can write some sort of expression for the reaction rate, which is something like A to the alpha, the concentration of B to the beta, okay? Now, and these alpha and beta are different, okay? I'll just write it here from the stoichiometric coefficients, okay? So you may be asking, what determines, okay, the reaction rate of the global process? Who gives me alpha and beta? And that's quite interesting. So let's see if in these 5 minutes I can show you. Well, the reaction rate of a global process, what determines it? Well, you can think of the global process that you can see here as a sum, okay, of elementary processes. So this is actually hiding, okay, this reaction here that you see in the global sense, it's actually hiding a series of elementary reactions. There are actual collision events between molecules, okay? And so this is a global representation of what we call a chemical kinetic mechanism, or a reaction mechanism, where by mechanism I mean more than one elementary reaction, okay? So what do you think the global rate will depend upon? Well, generally speaking, if you have a sequence of events, the overall event will be as fast, okay, as the slowest event. Think about it. If you have a series of cars, okay, piled up, one in front of the other, okay, driving on a road, and you have a bunch of, this is what I always say, of Ferraris, right? They want to go really fast, but what if you have one very small, very slow Cinquecento car, okay? Well, the whole thing is going to go as slow as the Cinquecento, even if you have a Ferrari, okay? And I can give you an example. For example, I'd introduce this, I'll give you this example here of a global process. Forget what this means. It's absolutely irrelevant. It's just okay. This is a global process. If I want to write down my reaction rate, this will be, and be careful now, K times NO2 to the power of 1, not 2, okay? Times, sorry, this is F2, okay, fluorine. At times the concentration of F2. So you see this cannot be an elementary reaction because alpha and beta, okay, are not equal to Ni1 and Ni2, okay, or not equal to the stoichiometric coefficients, okay? So not elementary, okay? So in fact, what we actually have is that this global mechanism is actually hiding, okay, 2 elementary steps, okay, which I'll write now. This is 1. I'll write down the reaction rate constant here, K1 over the arrow. And the other one is F plus NO2. This is K2 and NO2F, okay? It turns out, and as you can see now, the sum of this overall the F and F kind of is an intermediate species that kind of cancels out if you sum these two, and you get essentially 2NO2 plus F2 is equal to 2NO2F. Okay? And it turns out that this process here is slow, and this is fast. Why? Because essentially, K1 turns out to be smaller than K2. So this is what is driving the whole system. It's like our Cinquecento, okay? Is rate limiting. And in fact, okay, look at this reaction rate. It's exactly equal. It has the same expression as this one. So the overall global process inherits, okay, the reaction rate of the slow elementary sub-step, okay, which is, let me write it here, 2 elementary steps. Okay, I hope that's clear, but I'll get back to it on Thursday. Okay, I'll let you finish writing down and think about it, and if I'll get back to it on Thursday because I did it very fast. Okay, and now I will close my lesson. Okay, and hopefully I can sort of catch up.
Scusi, professore. Una domanda, ma giovedì c'è lezione oppure...
Ah, giovedì c'è... Aspettate.